Imagine Earth's atmosphere stretching like a giant rubber band, storing immense energy. When that atmospheric tension reaches its breaking point, it doesn't just sag, it violently snaps. This sudden release unleashes devastating weather, from intense heat waves to unprecedented blizzards. Understanding this hidden rubber band effect is key to predicting Earth's most extreme atmospheric tantrums. Weather patterns aren't simply driven by temperature differences and simple air movements alone. Instead, global air currents, like the jet stream, behave dynamically, constantly shifting and bending. These powerful, high-altitude rivers of air encircle our planet, influencing daily forecasts dramatically. For centuries, scientists observed their meandering paths, but a deeper mechanism remained elusive. Think of these colossal atmospheric flows as elastic bands, constantly being pulled and compressed. These movements aren't always smooth. They frequently encounter obstacles like towering mountain ranges. Such interactions cause the jet stream to buckle and contort, building up significant potential energy. This stored energy is precisely what leads to the rubber band effect in Earth's complex atmosphere. Recognizing this phenomenon helps us grasp why seemingly stable conditions can suddenly turn extreme. It explains those sudden, dramatic shifts in weather that leave entire regions completely unprepared. The primary driver behind this atmospheric stretching is the temperature contrast between the poles and equator. When this temperature difference is large, the jet stream flows strongly and relatively straight across continents. However, as polar regions warm disproportionately, this temperature gradient weakens significantly over time. A weaker gradient causes the jet stream to slow down and develop much wavier, more exaggerated loops. Imagine a garden hose with water pressure dropping. The stream becomes less focused and starts to wander. But that's not the strangest part of this intricate atmospheric dance. This meandering traps weather systems for extended periods, creating persistent heat waves or endless rain. These amplified waves can become so distorted they essentially pinch off isolated high or low-pressure such cells.
Scientists call these persistent features blocking patterns because they block other weather from passing through.
Isolated high or low-pressure such cells blocking patterns are like knots in our atmospheric rubber band, preventing smooth flow and building pressure. Wait until you hear what happens when these tightly stretched atmospheric bands finally release. This tension builds up over days or even weeks, pushing the atmospheric system past its elastic limit. When the rubber band finally snaps, the release of stored energy is incredibly rapid and powerful. One well-documented example involves sudden stratospheric warming events directly impacting the polar vortex. This warming can violently displace the polar jet stream, sending its icy grip much further south. This displacement brings extreme cold to regions accustomed to milder winters, shattering temperature records. And then something unexpected often happens, amplifying the initial climatic disruption. This sudden shift can also cause the jet stream to rebound with unusual force in the opposite direction. Such a rebound creates a whiplash effect, rapidly transitioning from extreme cold to unseasonable warmth. This dynamic, snapping mechanism isn't limited to cold outbreaks. It also drives intense heat domes. These domes form when a persistent high-pressure system gets locked in place, baking regions for weeks. The trapped air heats up, expanding and intensifying the heat, much like a pressure cooker. But the long-term implications of these atmospheric gymnastics are truly profound for human society. This stretching and snapping explains why some regions experience relentless drought, while others flood uncontrollably. The phenomenon creates a domino effect across the globe, connecting distant weather events surprisingly. It highlights how delicate Earth's atmospheric balance truly is, easily disrupted by subtle changes. Understanding this complex interplay helps meteorologists refine long-range weather predictions for critical planning. It allows them to anticipate extreme events with greater accuracy, providing crucial early warnings. This predictive power is vital for agriculture, disaster preparedness, and maintaining global economic stability. The rubber band effect demonstrates the interconnectedness of all atmospheric elements on our dynamic planet. It's a powerful reminder that Earth systems are not static, but constantly evolving and responding. The consequences of these atmospheric snaps are felt across continents, affecting millions of lives directly. Prolonged droughts devastate agricultural yields, threatening food security for vulnerable populations worldwide. Conversely, sudden, heavy rainfall events trigger catastrophic flooding, destroying infrastructure and displacing communities. Heat domes can lead to unprecedented public health crises, particularly among the elderly and infirm. Energy grids struggle under extreme demand, resulting in widespread power outages during critical times. The economic costs associated with these extreme weather events are staggering, totaling billions annually globally. Insurance companies face immense payouts, sometimes struggling to cover the increasing frequency of disasters. Ecosystems also suffer dramatically, with species struggling to adapt to rapidly changing local climates. For instance, coral reefs bleach under sustained heat, while forests become more susceptible to wildfires. The rubber band effect highlights our planet's vulnerability and humanity's urgent need for climate resilience. So the next time you hear about extreme weather, remember the Earth's atmosphere stretching and snapping. This rubber band effect isn't just a metaphor, it's a powerful explanation for our planet's dramatic climate shifts. Understanding these complex dynamics is crucial for building a more resilient and informed global society. If you found this explanation fascinating, hit subscribe for more incredible insights into our amazing world. And let me know in the comments what other hidden forces of nature intrigue you most.